Good afternoon. Thanks for coming to our senior design thesis presentation on design analysis and optimization of multi-units. I'm Abraham Neese.
I'm Sohail Reddy.
And I'm Shani Powell.
I've been to the airport recently and checked out some of the wings on the terminal. If you look at the wing tips, you'll see it's very popular to have horns up winglets at the end of many of the aircraft today. Some more recent trend is to incorporate split configuration going up and down. In our presentation, we're going to discuss a split configuration with actual wing tips, with spikes at the end of the wing tips here. These spikes actually make a big difference in the flow. In terms of a regular wing, this particular wing configuration was designed by a 2010 design team at FIU here, and they've done the blended wing here to optimize that. In our presentation, we're going to investigate a split configuration as seen here on our prototype. The difference in pressure on the wing between the upper and the lower surface creates a pressure gradient at the end of the wing tip, and this creates vortice effects. These vortice effects induce more drag on the aircraft. This induced drag on the aircraft will be has a lot of challenges to it. We're going to investigate the approaches with different types of winglets. If you go to the next slide. Again, some of the benefits again are going to be more fuel efficient in general. Another benefit would be to have a reduction in the trailing vortices on other aircraft. If you see the diagram here at the vortices that are trailing the wing on the aircraft, there's so much energy that's consumed just in generating these vortices. If there's any aircraft in its way in the sky that may be a little smaller than this aircraft, they can actually flip it over in mid-flight. If there's a car, maybe on the runway, you can actually flip a car over just from the actual energy that's being dissipated. Some of the other benefits are to reduce the thrust settings at takeoff and for aircraft, just because you'll have less, and you'll have a higher lift to drag ratio. An indirect benefit would be some reduction in noise in the aircraft area, the airports, and of course emissions from carbon emissions. Our analysis, our main analysis for the CFD components was done in software called OpenFOAM. Our optimization was done in software packages called Frontier.
So our geometry was generated by a Fortran code E300, and this was written by Dr. Helmut Sebeski. And what it basically does is that we have a predefined analytic functions, and we use these to create the graphs that you see on the far left of your screen. Now from these curves, a combination of these curves, they create a cross-section. And then when we combine these cross-sections with these curves, we end up getting a 3D surface, which is actually our winglet model. Now, if we could find a way to relate the parameters that we use in our design to each other, we would reduce the number of input parameters as well as we would reduce the number of initial population. So in our case, what we did, we had 8 directly controlled parameters, and they were the directly controlled ones were the leading edge sweep, the trailing edge sweep, and then when we directly control those parameters, we indirectly control the taper ratio of our wing. And then we also control we directly control the cant angle right here, which indirectly control the winglet span. And then we control the spike length, which is right here, and we applied all these parameters to both the upper winglet and the ventral fin, which is the lower winglet. And I should also point out that we have the ventral spikes here that we added to our winglet.
For some geometry preprocessing, since the code to generate our geometry was made in a Fortran code, there were some holes in geometry, namely in the trailing edges and the winglet tips. These holes can affect the meshing process where the cells can creep into the actual geometry. To avoid this problem, we closed the actual geometry with software called MeshLab, and that's
OpenFOAM. All of our CFD analysis will be carried out in a software called OpenFOAM, which stands for Open Source Field Operation and Manipulation. This shows a basic case structure for an OpenFOAM file. It has a 0 directory, which houses your initial and your boundary condition. A constant directory, which houses your mesh, your STL geometry, and properties such as transport property, turbulence model, etc. The system directory houses your discretization scheme and your solver settings, along with mesh settings. Our analysis is carried out at 0.25, Mach 0.25, which is about 85 miles per hour, meters per second, excuse me, at an angle of attack of 11 degrees to simulate takeoff conditions of aircraft. It is an open source software, so it is readily available on the Panther cluster, which allows for high performance computing. Computational grid generation. OpenFOAM has two meshes, built-in meshes, block mesh and SnappyHex. Block mesh creates a fluid domain, SnappyHex extracts the geometry from the fluid domain to say external flow. This here is an example. This is your block mesh, the fluid domain with the geometry embedded inside. Then SnappyHex carves the inside out, so you just study the external flow. This is our winglet after it's been meshed. You can see the SnappyHex captured beautifully the spiked, very sharp objects, which for other meshes would be very, very problematic. So as mentioned, our CFD analysis will be carried out in OpenFOAM. We'll be solving seven equations: the mass conservation, the x-linear momentum equation, the y-linear, and the z-linear, along with two transport equations from the K-epsilon turbulence model. This model we've chosen to model the vortex shedding at the wingtips.
Alright, so here is a CFD picture of our wing, and we're actually looking downstream. So this is a naked wing, it's not optimized, but we just did the CFD in OpenFOAM. So what you could see is at the wingtip, the airflow looks quite chaotic. And we ended up with a lift to drag ratio of less than 5 in this case. And this is a random, non-optimized winglet, but in this case, we added the winglets at the wingtip. And what you'll see is that we ended up with a lift to drag ratio of 5.44, which is significantly greater than the wing without the winglet. All right, so this is an optimized blended wing. We removed the ventral fin, which would usually be at the bottom. So it's just, right now, just the upper surface of the winglet. And we see here that there's a smoother transition of flow over the upper surface of the wing. And this gave a lift to drag ratio of 5.38. So even though this is optimized from the previous slide, it shows that just by adding the split winglet, it produced an even higher lift to drag ratio of the optimized wing. Now here is the optimized split winglet. In this case, we don't have the spikes at the tips, but after optimizing this so far has produced the highest lift to drag ratio of 5.58 and highest coefficient of lift of 0.69 and the lowest coefficient of drag of 0.12.
Okay, multi-objective optimization, the whole goal of this project. Our multi-objective optimization was carried out in a software called ModeFrontier, and our method of choice was response surface approximation coupled with the genetic algorithm. We have 8 design variables, basically the 8 directly controlled parameters of the winglet itself, both the upper and lower, with 4 objectives. The simultaneous objectives being maximizing coefficient of lift, minimizing coefficient of drag, minimizing the absolute value of the coefficient of moment, and maximizing the lift to drag ratio. Response surface. Our Navier-Stokes solver takes 15 hours to solve the flow field around the geometry to give out our aerodynamic coefficient. For this reason, an approximation model, a meta model was used, and it's called response surface. We basically created the response surface using Gaussian radial basis functions, which have been proven to be accurate. In our case, within 2% of error from the actual Navier-Stokes solver itself. We created the response surface using 40 randomly created initial population. Population meaning our candidate winglet design, and this randomly was created using a snowball sequence. Genetic algorithm. Now we have the response surface, we have the objective function space. We need an effective method to search the space for our optimum design. For this reason, a genetic algorithm, in particular the non-dominated sorting genetic algorithm, NASCA2, developed by DEV, was employed. It features crossover, a random combination of design, basically of parent genes to create a new individual, and mutation, the random alteration of one of the 8 parameters to create a new individual. As you know, in multi-objective optimization, you do not have any one optimum design. You always have a selection of design, best trade-off or Pareto solution. The collection of these are known as Pareto front. Here you can see in blue is our initial population, the population used to create the response surface. The red was our virtual Pareto design that were found by the genetic algorithm after searching the response surface. We have selected Pareto 2996 as our Pareto design that satisfied all 4 of our objectives. These blue population took 2 days to create, basically 2 days. One case took a day. All 4,000 of these were created in less than 30 seconds using the approximation.
All right, so we selected part 2996 as our best design. And if we compare the optimized design, which is on the right here, and the base design, what we see is a significant increase in the lift to drag ratio of 5.69 compared to 5.44. We also see a significant improvement in the coefficient of lift compared to the base design, and also an improvement in the coefficient of drag when we compare to the base design.
So to put all these coefficients into perspective, let's compare them by percentages. This column shows the percent increase for CL, CD, CM, and the lift to drag ratio. We had a 6% increase, 7% increase in the coefficient of lift over the naked wing, a 7% decrease in drag, a 31% decrease in the coefficient of moment, and about a 15% increase in the lift to drag ratio.
A bit about manufacturing. Since we had used a 3D printer to print our prototype, due to the size constraints of the printer's output, we had to make it in segments. So we actually had made 5 different sections. The bottom part here is the actual end part of the wing, if you look at the bottom of the prototype. And the top part also had ears together, and you flip that over and you get our prototype. Due to the nature of 3D printers, it creates infinitesimal layers of printing. It gives you a lot of ribbed edges. In order to smoothen that out, have a smooth surface, we had to fill that in with epoxy filler and sand that down a couple of times until we got this nice finish. Another feature here you can see is we had put a mounting bracket on the bottom surface of this wing to put that in our wind tunnel for validation. Our actual model is at 18 inches long. That's due to the size constraints of the wind tunnel at Embry-Riddle University's wind tunnel. The actual speed that we carried out, our validation was at approximately Mach 0.1, which translates to about 34 meters per second, which is roughly about 70 miles an hour. There, we actually had servo motors in the wind tunnel that was able to modify the angle of attack, which means the flow, the stream of the air in the wing. We started at -4 degrees and we carried it up all the way to positive 16 degrees with increments of 2 degrees each. At all these angles, we kept the speed constant. We had done this for all our different configurations, namely just the naked wing without any winglet on the end. And then we had done the same test with just a blended winglet model. And then the final, our optimized design, the split scimitar configuration we can put here, which you can see the prototype. In order to process all this data, there's a software called LabVIEW that was connected to the wind tunnel, and that software gave us out our data, which we're seeking, which is namely coefficients of lift, coefficients of drag, and coefficients of moment. We're going to see in the next slide here all the data that was processed. Namely for the green, you can see that's reflecting our split scimitar configuration. The coefficients of lift are higher in our split scimitar configuration over the red one, which reflects the naked wing, or the blue one, which is just the blended. Inversely is true as well for the coefficients of drag. The green one, which is our split scimitar, has the lowest coefficient of drag as opposed to the naked wing or the blended wing, which has a higher coefficient of drag. Another interesting feature, if you look over here at the angle of attack of 12 degrees, the blended winglet, which is the naked wing without any winglet, had given a stall at angles at 12 degrees. When we attached our winglets at the end, especially the split scimitar, we were able to go for another few degrees before we started seeing flow separation, which is part of stall.
Okay. Comparing our experimental to our numerical results. Well, for accurate comparison of scaled model, the non-dimensionless numbers have to match. In our case, it'll be the Reynolds number. This table here shows for the numerical value, which was in open foam, the Reynolds number is 48 million. With the experimental value, which is in wind tunnels, it's about 300,000. They don't match. To compensate for this, what we did was we ran our scaled down model in the same environment as it would be in the wind tunnel, but in open foam. So numerical analysis of the scaled down model. And we'll see the results to that. So here we can see the red, this is for the naked wing. The red shows the numerical, open OF, meaning open foam. and the green shows wind tunnel, WT. You can see there's a good correlation between numerical and experimental results for both coefficient of lift and drag, as well as the coefficient of moment. The numerical analysis was able to capture this wingtip stall quite accurately. One key thing to keep in mind, very important, is this 10 degrees. The naked wing is stalling at 10 degrees. For our Pareto 2996, same, analyze the scale down model in OpenFOAM. Again, a good correlation between lift, drag, and here you can see the coefficient of moment is the wingtip is stalling at 12 degrees, 2 degrees after the naked wing. This gives much more stability in the post-stall region for an aircraft.
Our cost analysis, just to keep our costs low, we were able to keep it quite low by using software such as OpenFOAM, which was free. We were also able to use Mode Frontier free of charge due to contributions from the manufacturer. Also, we're fortunate to validate our design at Embry-Riddle's wind tunnel testing free of charge, which saves significant costs. Our total cost ran at about $180 just for the rapid prototyping. That's the latest cost.
So in conclusion, we have achieved all 4 of our objectives. We've minimized coefficient of drag and coefficient of moment, and maximized coefficient of lift and lift to drag ratio. Our experimental results confirm our numerical results that we obtained from OpenFOAM. We have demonstrated a stable behavior of the wing with the wingless throughout the range of angles of attack. We have also shown a cost-effective method of improving existing design. Simply the addition of the lower element to an existing blended wingless, which is being applied to which is being used in the industry today, leads to improved performance. Now this is the punchline. A 2% decrease in induced drag led to $65 million in savings for United Airlines in jet fuel alone. We had a 4% decrease in drag, so I'll leave the correlation to you. This work has also resulted in a paper at the World Conference on Computational Mechanics that will be presented this July in Barcelona. So future research. We might be able to obtain more improved performance by modeling birds, the perfect flying creature. This will result in feather-like winglets. We could possibly add, such as seen over here, we can possibly have deforming bodies with time using smart materials. We can analyze the effects of winglets on the entire aircraft, engines, tails, fuselage included. We could also introduce more geometric parameters to achieve a more accurate definition of the wing.
Further applications can be minimal devices, just on their blades to change the shape and add different winglets. We wouldn't be applied to turbines because there's a lot more turbulence there. Or hydrofoils where you have a keel going into the water. At the end of the keel, you can have at the end something split configuration that will keep the boats having better buoyancies.
We'd like to acknowledge Professor George Dulikovic, our advisor, for his guidance in this project. Professor Sobieski, he helped us parametrize the geometry. He's actually an engineer for DLR Aerospace in Germany. Professor Carlo Poloni, founder and CEO of SOK, for providing us Mode Frontier free of charge. He's a professor at Trieste University in Italy. Abbas Abdulli for his help on numerical analysis and OpenFOAM software. Ryan Lucia, he's an undergraduate student actually. He helped us rapid prototype our design. And the staff at Embry-Riddle University, in particular Professor Nana Manigon and Hassan Khalifi, for providing us their wind tunnel free of charge. And this concludes our presentation.
I'm going to start off with 2. I'm an aviator. I've never heard of split scimitar. Tell me about that.
Okay. So the word scimitar in Japan means sword. It's basically a sword with a curled back tip. So split meaning one going up, one going down, and the scimitar part comes in at the tip cap, where the tip of the blended is swept back and to a sharp point. That's the whole idea. The tips themselves help reduce drag and streamline the flow.
So that name originated from you guys, or did you get it from
No, it's actually being investigated by Aviation Partners right now.
Okay.
United is supposedly the first recipient.
And seeing that this is so novel, have you guys initiated discussions yet with Boeing and Airbus?
Yeah, no, we have.
All right, those are my questions, sir. Who wants to go?
A couple of questions. I noticed a disparity in your synopsis of what you stated as was your goal versus your purpose in your abstract. You might want to take a look at that. Your synopsis indicates that your goal is to optimize the configuration, which you're doing. However, in your abstract, you say your goal is to formulate an optimization procedure. So I was a little confused on whether you were trying to find a procedure or actually a configuration.
Okay, so the procedure for optimization is a method of optimization. Even though we have formulated a method, it still has to be validated if it works. So a goal for optimization is one thing, but to validate it, we need numerical comparison. So if you go back to our numerical workflow,
So what is the, were you trying to find an optimization procedure or
No,
were you trying to
no.
find a configuration?
we're trying to find a configuration that best satisfies all four objectives that we had for ourselves.
Very good. You have a slide there, sorry for the old language here, that talks about experimental comparison. Can you put that
Sure.
up? For us over 50, those green lines are horrible. You can't see them at all.
Actually-
There are green lines on there, right? They're
Green dots.
Yeah,
Yeah.
this wasn't the PowerPoint that was supposed to be uploaded, but this is
Oh.
what we worked with.
Okay, very good. I noticed in your report, you talked about who was assigned what tasks. It looked like there was a lot of isolation. Abraham was the only one who did manufacturing, is that correct?
For the most part, I saw the manufacturing. Everyone was involved in every part of it.
Okay, and then I have, so how did the optimization?
I did the optimization.
I was surprised that I didn't perceive more interaction with various elements.
Okay, so.
Is that a misperception?
That is actually is a misperception. Oh, I wouldn't say it's a misperception. I'll just tell you what we did. So Sinead took care of the CAD design. Okay, and Abraham also did the CAD design. He basically did the pre-processing of the geometry as well. So we all have to understand the Fortran code and how it worked, how each software worked. And then with CFD analysis, you need as many processes as you can to run parallel runs. So all three of us did CFD analysis, and optimization was carried out by me.
Very good, thank you.
All right, any other questions?
And my question is on risk management.
Mhm.
Did you look into FMEA or any kind of way to ensure that, you could have greater drag lift ratio, but it might be an unsafe situation if you get going a barrel?
Okay,
Really
so
dangerous.
you're talking about in structural part of it as well, is correct? Is that correct?
Correct.
Okay, so for that, the internal structure of the wing would have to be known for it to analyze it efficiently. But what we've proven is the wingtip is stalling much later with the winglet, which means the aircraft is not pitching up so violently, which in turn reduces the stress on the wing and the internal components themselves. So
But the
that's-
winglet design itself is adequate to take the max load conditions it's going to take?
I'm sorry, could you repeat the question?
The winglet itself, I think, in particular the tail,
Uh-huh.
is capable of handling any and all.
Oh, you're
of-
talking about the tip, yes?
The tip.
Okay, so the tip doesn't really produce lift. It just streamlines the flow. We saw when you compared the
There's
without tip.
no load being applied at the tip of that wing by having the tip?
We have sideways force, but for that, the internal structure of the tip would have to be known. When you retrofit a winglet, it has internal structure which is designed by Boeing or whichever aircraft. Structural engineers, exactly. So that would have to be strengthened for the winglet itself. So
Okay,
for
so
that,
in reality, there's a whole nother leg of work that needs to be done to do the structural analysis on each and every one of these before you could ever use this concept.
well, the structure would have to be tied in with the optimization. Because you can have one of the constraints reducing weight of the structure while maintaining its.
Let me help them out with that. That's a different process. They've done the aerodynamics.
Yeah.
So now they need to feed that information to the structural engineer who will make sure it works. It's almost like they're the architect, and you gotta get, the architect's gotta give his stuff to the structural engineer to make the building work.
So give it to the city
Thank
to
you.
fix all the ills of the architect.
Thank you.
Any other question? I guess that's it. Well, thank you very much. Doctor, do you have a question or a comment?
Couple of questions. Now, you said that the entire cost is something like $180 or something like that. That's because of the beneficence of the people over at Henry Riddle and as well as all. If you didn't have that beneficence, how much would it be? Maybe how much?
Per hour at the tunnel, we approximated it would be like at least $100.
Yeah. But for the wind tunnel itself, it would be about 1,100. Combined with most material, it would be about 2,500. For this scale that I'm on.
Okay. The other question I had was, okay, now that you've taken off and you've shown reduced, what kind of behavior do you see at normal operating speeds? When you're flying normally 500 miles an hour, what kind of behavior do you see in that?
So our
What do
part,
you think is going to happen?
our part was optimizing it for the takeoff condition. We have analyzed it at maximum at 0.5 because the solenoid that we have is very unstable at transonic speed. So we don't have the computation resources to analyze it past 0.5 Mach.
We do expect to see some symmetrical results.
Using from statistical data, we expect similar behavior throughout the range of speed.
I can add to that. I mean, based on current wing lift design and performance, they're gonna get better range, better performance, more stability. So there's some real tangible benefits if they can reduce wing lift vortices with what we need.